As discussed earlier in the last lecture, in this lecture initially we will go through some more useful functions and we will check the Laplace transform of those functions. The first one we will cover is the error function. Let us see what is error function. The error function ERF of t is defined by this one. ERF function ERF of t is defined by ERF of t equals 2 by root pi 0 to t e power minus x square dx. Please see from here, ERF of t equals 2 by root over pi 0 to t e power minus x square dx, and the graph of this function also we have written over here. Now, ERF of 0, obviously at t equals 0, the value will be equals to 0. Next, you see the ERF of infinity. At t equals infinity, what happens? 2 by root over pi. So, it will be 0 to infinity e power minus x square dx. And this equals, you can write down 2 by root over pi. If I substitute u equals say x square, then this will be transformed to 0 to infinity e power minus u into u to the power, it will be minus half by 2 into du. And so that this minus half you can write it as, this minus half you can write it 1 minus half. So that I can express this function as a gamma function directly. So, I can write down 2 by root pi into gamma half, 2 by root pi into gamma half, and as you know value of gamma half is 1 by root pi. So, that it value this 2 will not come, this 2 is being cancelled. So, this will be 1 by root pi into gamma half, and gamma half is root pi. So, that the value you will obtain as 1. So, please note that the value of the ERF function ERF of t as t approaches infinity is equals to 1. So, ERF of infinity, as I was showing you, this is equals to, this becomes 1. There is another function which I call complementary error function. You see, ERF function is from 0 to infinity, 0 to t, 2 by root pi 0 to t e power minus x square dx, and the ERF of complementary error function is defined as 2 by root pi t to infinity e power minus x square dx, and this is I can write it into two ways, 0 to infinity e power minus x square minus 0 to t I can make it, since the integral is from 0 to t to infinity. So, I can break it 2 by root pi into e power minus x square. I can write down 0 to infinity e power minus x square minus 1 by root pi 0 to t e power minus x square. So, that this is nothing but this I can write down ERF of infinity minus ERF of t, and ERF of infinity already in the last slide we have shown that the value is 0. So, that this is 1, in the last slide we have shown 1. So, that the complementary error function is nothing but 1 minus the error function of t. So, complementary error function of t equals 1 minus error function of t, what we have shown over here. Now, what is the Laplace transform of error function of t? Those things we told certain properties. This, please note that this error function and some more functions are very useful for solving various kind of engineering problems also. So, this equals Laplace transform of 2 by root pi into 0 to t e power minus x square into dx, and this equals 2 by root pi, I can bring it outside using integral property of Laplace, integral theorem of Laplace transform. I can write it as 2 by root pi into 1 by s into Laplace transform of e power minus x square. and Laplace transform of e power minus x square, I can write it 1 by s into 0 to infinity e power minus s x into e power minus x square dx. This again using the basic definition of Laplace transform. So, that this again I will write down 2 by root pi into 1 by s e power s square by 4, I am just explaining, into 0 to infinity e power minus x plus s by 2 whole square, I am just writing into dx. My aim is to make it to some known function. So, that I am multiplying e power s square by 4 here, and this e power s square by 4 I have taken over here. So, that they will be nullified over here. Now, you can take x plus s by 2 equals say u. If you take x plus s by 2 equals u, in that case this will be converted into 2 by root pi 1 by s e power s square by 4 into s by 2 to infinity, s by 2 to infinity e power minus u square into du. So, once I am writing this, what is this? S by 2 into e power minus s u square du. You recall what is complementary error function? ERF of c of t, that is t to infinity e power minus x square dx. So, this integral, this one we can write down 1 by s into e power s square by 4 into complementary error function, that is ERF of c of s by 2. So, the Laplace transform of ERF of t, this is equals to 1 by s e power s square by 4 into complementary error function of s by 2. Let us see, come back again. So, just whatever we are saying, to Laplace transform of ERF of t is Laplace transform of 2 by root pi into this one. From here I am obtaining 2 by root pi 1 by s 0 to infinity e power minus s x minus s square. This I am writing in this form, which is nothing but s by 2 to infinity, and this equals 1 by s e power s square by 4 into error function of complementary error function of s by 2. So, Laplace transform of ERF of t can be written in terms of the complementary error function of t, and which is in terms of s by 2. Now, let us see what would be the Laplace transform of error function of root t. Your f t is equals to ERF of root t. And what is ERF of root t? By definition, 2 by root pi 0 to root t, since root t is there, e power minus x square dx. And of course, we are assuming that Laplace transform of f t, this is nothing but say f s. So, once I am obtaining this, Laplace transform of f t is f x, and ERF of root t is 2 by root pi 0 to root t e power minus x square dx. So, that from here directly you can say your f 0 will be equals to 0 like earlier cases, and using Leibniz integral theorem f dash t I can write down 1 by root pi will come into t is there. So, t to the power minus half will come into e power minus 1. Using Leibniz formula, I will obtain f dash t by using the integral formula. I cannot tell that this is equals 1 by root pi t to the power minus half into e power minus 1. So, I will start from here, Laplace transform of say f dash t. This is equals to 1 by root pi f dash t, already we have evaluated, Laplace transform of t to the power minus half into e power minus 1. So, that you can tell that Laplace transform of f dash t, this is equals to 1 by root pi into f of, where f 1 of s plus 1, where f 1 s is nothing but I am saying that Laplace transform of t to the power minus half. F 1 will be Laplace transform of t to the power minus half. So, I have to find out basically this one. So, once I am obtaining this, Laplace transform of f dash t equals 1 by root pi into f 1 s plus 1, where f 1 s is Laplace transform of half. So, that you can write down Laplace transform of f dash t, this is equals to 1 by root pi into t to the power n, I know Laplace transform of t to the power n, I know it. So, from here it will be gamma half by root over s plus 1. So, that here Laplace transform of f dash t is equals to what? Now, s f s minus f 0. This is equals to s f s minus f 0, and this gamma half is root pi. So, that you will obtain 1 by root s plus 1. So, s f s minus f 0 is equals to 1 by root over s plus 1, f 0 is already 0. So, from here you can write down now your f s is equals to 1 by s into root over s plus 1. So, since I obtained the f s, so I can tell that Laplace transform of ERF of root t, this is equals to 1 by s into root over s plus 1. So, Laplace transform of ERF of root t, this is equals 1 by s into root over s plus 1. So, the quickly if I go through this, just f 0 f dash t I am finding out. From there, using the theorems, I am getting Laplace transform of f dash t is f 1 s plus 1. From here, I am finding the Laplace transform of t to the power minus half, I am writing, and then I am getting f s is 1 by s into root over s plus 1, since f 0 is also 0 and gamma half is root pi. So, that Laplace transform of ERF of root t is 1 by s into root over s plus 1. Now, let us see quickly the Laplace transform of ERF of 2 root t. The last one was Laplace transform of root t. So, already I know that the Laplace transform of ERF of root t is 1 by s into root over s plus 1. This I know it. Using the property, now I can tell that Laplace transform of ERF of 2 root t is equals to Laplace transform of ERF of root over 4 t. I can bring 2 inside the root over, and once I know this root over 4 t, so t will be replaced over here. So, I am getting 1 by 4 into 1 by s by 4 into root over s by 4 plus 1. I have used this property, Laplace transform of f a t is 1 by a f of s by a, this is known to us, and from here I can tell by simple calculation the Laplace transform of ERF of 2 root t, this is equals to 2 by s into root over s plus 4. And this one from here again, therefore, the Laplace transform of t of ERF of 2 root t. In the last one, what I obtained? I obtained Laplace transform of ERF of 2 root t. So, now I am finding out the Laplace transform of t into ERF of root t. This is nothing but minus ddS of Laplace transform of ERF of 2 root t. So, dd minus ddS of ERF of 2 root t, I know it already. So, I am just substituting the value, and if I make the differentiation, I will obtain the result as the 3 s plus 8 divided by s square into s plus 4 to the power 3 by 2. So, this is your one function which we call the error function, and this error function is used in various engineering problems. We always come across this error function, and once I am getting the error function, if I know the Laplace transform of this error function, it will be useful for me to solve various problems. Now, unit step function or Heaviside function, this already I have discussed in other form, u t minus a equals 0 for t less than a and 1 for t greater than a. I have done it. So, just I am showing it once more. Laplace transform of u t minus a equals 0 to infinity e power minus s t u t minus a dt. This I can break it, since the function is defined in two range, in 0 to a it is 1 and a to infinity it is other. So, I am breaking the function into two, 0 to a to infinity. In 0 to a the value is 0, in a to infinity the value of the function is 1. So, it is simpler, and if I evaluate this, I will obtain the result as e power minus a s by s. Please note this one, that the value of the unit step function, Laplace transform of unit step function of that category is e power minus a s by s. There is another important function which appears frequently in various engineering problems, which we call as impulse function or Dirac delta function. You see the figure here. The function is defined like this: f epsilon t, this is equals 1 by epsilon whenever t lies between 0 to epsilon, and the value is 0 whenever you are coming over here. So, in this case basically it is creating a problem over here. It is creating a triangle something like this, such that 0 to infinity f epsilon t dt or equals 1. I am just explaining. So, please note that Dirac delta function is defined like this: f epsilon t equals 1 by epsilon when t lies between 0 to epsilon, and 0 whenever t greater than epsilon, and 0 to infinity f epsilon t dt, this is equals to 0 to epsilon f epsilon t dt, this is equals to 1. You see this area 0 to epsilon, it is varying, t is varying a very small range, that is epsilon is a very small quantity, and the function is going up to 1 by epsilon. Now, what happens? Basically, we say that a very large force is being is acting for a very short period. In this case, what happens? Whenever epsilon approaches 0, if you see the figure, your figure is something like this. This is 0, this is epsilon, you are having 1 by epsilon over here. So, whenever epsilon approaches 0, what happens? The height approaches to infinity, the height will approach the infinity in such a manner that the area of this rectangle, this is a rectangle, and area of this rectangle always will remain 1 only. Please note this one, because area of this rectangle is epsilon into 1 by epsilon. So, it is 1, area of this rectangle always will be 1. So, please note, as epsilon approaches 0, your height is approaching infinity indefinitely, and the width decreases. Width means this epsilon value decreases in such a fashion that the area always is 1, and that only we are writing as epsilon approaches 0, 0 to infinity, this Dirac delta function is equals to 1. F epsilon t dt is equals to 1, or the area always will remain 1. So, the impulse function sometimes we write in this way also: f epsilon t minus a, this is equals 1 by epsilon whenever t lies between a to epsilon, and it is 0 otherwise. If epsilon approaches 0, then as epsilon approaches 0, then what will happen? This f epsilon t minus a is known as the Dirac delta function, which we denote sometimes by this also, delta t minus a. This is equals infinity when t equals a, and 0 for t not equals a. So, please see this one, at t equals a the value is 0, at t not equals a value is 0, at t equals a value is infinity. So, that you are writing in such a fashion that 0 to infinity, this delta t dt, this value always will be equals to 1. So, as I told you at the very beginning that the very small force large force is acting for a very small period. So, that we are defining that function as a Dirac delta function. So, two definitions are there. One we have told from 0 to epsilon this thing, and other one is this epsilon, and in this case 0 to infinity delta t dt is 1, or sometimes we define it as f epsilon t dt, this is also equals to 1. So, just as I told you, impulse function can be written as this also, t lies between a to epsilon, and from there I can write down delta t minus a equals infinity at t equals a, and at t not equals a the value is 0. Therefore, 0 to infinity delta t dt, this is equals to 1. As I told, area always should be equals to 1. So, 0 to t 0 to infinity f t into f epsilon t minus a, this I can write it as a to a plus epsilon f t into 1 by epsilon into dt. And if I use mean value theorem over here in a very eta which lies between a to a plus epsilon, I will obtain a plus epsilon minus a into f eta into 1 by epsilon. So, that ultimately you are getting f the result as f eta. So, please note that 0 to infinity f t into f epsilon t minus a dt, this is equals f t. Now, you see limit epsilon approaches 0, 0 to infinity f t into f epsilon t minus a into dt, this nothing but limit epsilon approaches 0 f of eta, as I told you. So, from here you can write down 0 to infinity f t, this again I can write it as delta t minus a Dirac delta function also, dt, this equals nothing but this will be equals to f a on this side, and also from here I can tell that 0 to infinity f t into delta t dt equals f 0. So, from here limit epsilon approaches 0, 0 to infinity f t into f epsilon t minus a dt, which I am writing as from the earlier working limit epsilon approaches 0 f eta. So, that whenever 0 to infinity I am writing if epsilon approaches 0, f t into this will be a Dirac delta function dt, and this value will be equals to f a at that particular point. And whenever a is 0, then I will obtain f t into delta t dt, this is equals f 0. So, Laplace transform of Dirac delta function equals Laplace transform of Dirac delta function delta t minus a, this is equals 0 to infinity e power minus s t into delta t minus a dt. Directly using the property I can write down, and using the property of Dirac delta function, the property which I shown just now, this is nothing but e power minus s a. So, you see Laplace transform of Dirac delta function delta t minus a, using simply the property of the Dirac delta function, directly I am writing e power minus s a, and Laplace transform of delta t, that is whenever your a is 0, then the value is equals to 1 for a equals 0. So, please note that Laplace transform of Dirac delta function, that is delta t minus a, is e power minus s a, and Laplace transform of delta t, this is equals to 1. So, just let us see from the earlier one, I got this one 0 to infinity f t into f epsilon t minus a dt equals f tau, and from here I am getting limit epsilon approaches infinity 0 to infinity f t into f epsilon t dt, and once I am getting this thing, therefore, from here I am writing 0 to infinity delta t minus a, this is nothing but a f a using the earlier properties. So, that 0 to infinity f t delta t is f 0 and limit Laplace transform of delta t minus a is equals to 0 to infinity e power minus s t into delta t minus a, and from here again I can, using the property, I can say that this is equals e power minus s a. So, that Laplace transform of delta t is equals to 1 by substituting the value a equals 0. So, as I told you, this is the Laplace transform of Dirac delta function. Now, let us see the application. We want to find out the Laplace transform of this function, say f t equals sin t into Dirac delta function of t minus pi by 4 plus pi by 2 t into Dirac delta function of t minus pi by 2. So, Laplace transform of f t, this is equals 0 to infinity e power minus s t sin 2 t into Dirac delta function of t minus pi by 4 into d t plus 0 to infinity e power minus s t into pi by 2 t into Dirac delta function of t minus pi by 2 into d t. And if I evaluate this, I know the value of these two functions separately. This will be e power minus s t into sin 2 t at t equals pi by 4 will come plus e power minus s t into pi by 2 t. Here t will be at pi by 2. So, directly I can write down the value of this e power minus s t into sin 2 t, because Laplace transform I know it of the Dirac delta function. So, it is e power minus s a was there, since this is the function. So, it will be e power minus s t into sin 2 t. If I evaluate this one, I will obtain e power minus s pi by 4 into e power minus s pi by 2, and this will be the result. So, if you see, the result is this one, and so it is very simple. Before this, I was knowing that Laplace transform of delta t minus a is e power minus s a. I am just using that formula in this example. I am writing 0 to infinity e power minus sin t into e power minus s t into sin 2 t, and this is nothing but then at t equals pi by 4 e power minus s t into sin 2 t plus this, and I will obtain this. So, please note in this case the Dirac delta function, again I am repeating it, the idea of a very large force acting for a very short time is of frequent occurrence in mechanics. To deal with such and similar ideas, Dirac delta function was introduced, and in mechanics it is this function is being used very frequently. And so, for this reason it is important for us to know the Laplace transform of this kind of function. So, just I told you we can define it by like this. So, Laplace transform of f t, directly you can write it like this. If I evaluate h by s into e power minus s a minus e power minus s b, also I can write down. Means the impulse function I can write it in various ways, and if I use any form I can obtain the Laplace transform of this one. Please note that here a is fixed and b is always tending to the value tending to a, and h is approaching in such a way that always this area h into b minus a, it is equals to 1. So, limit a b tends to a, h tends to infinity, h into b minus a, this is equals to 1. So, then limit b approaches a, h approaches infinity, Laplace transform of this is this, and if I evaluate the limit b approaches a, h approaches infinity, h into b minus a, that part will be 1, and this value if I evaluate 1 by s into e power minus s a. So that again I am getting the same result. Laplace transform of Dirac delta function is e power minus s a. So, whatever form of Dirac delta function is used, I have shown you the various forms, and from there we have obtained the Laplace transform of those Dirac delta function. Thank you.